Good morning, everyone. I am going to be, as Corey just said, be talking a little bit about vector-borne diseases and how our prediction of vector-borne diseases is changing as our non-analog climates. Non-analog climates is just a fancy term for climates that have never existed before, climates that we don't have previous data for. So climates that are moving into new ranges will be considered non-analog climates. And a vector-borne disease, so just to define a couple things, a vector is that guy right there. That is a Pulex irritans, or a human flea. Whenever I say vector, just think of a small bug, small insect, anything that is capable of transmitting a disease. And this guy, Pulex irritans, along with a couple other people, a couple other insects, are responsible for roughly about 17% of infectious diseases around the world. That equates to 700 million cases worldwide, with over 1 million of those, or roughly under 1 million of those, being fatal. A majority of these are collected in tropical areas and have kind of adopted the term neglected tropical diseases because they are in areas with low GDP growth and inadequate healthcare to actually address these issues. Now you might be thinking, why should we care about this? We have great healthcare, we have amazing vaccines and all these great things going for us in our first world country, but unfortunately, neglect can no longer be our option of looking at these. We have to kind of change the way that we look at these. So the biggest one in my research and what I looked at was various different mosquitoes who have become endemic to California. So there's the Aedes aegypti, Aedes albopictus, sorry, I always get that one wrong, and the Aedes nodoscriptus, which are all different types of very similar Aedes mosquitoes that can be found in a variety of different counties here in California and San Diego as well. Their lifespan actually revolves around water. So that's where the important part of climate comes into this, is the water cycle, or the life cycle of the vector itself is heavily dependent on water. They live to be roughly about 4 weeks, the adult females, but they spend the first week of that in water. So the water source is incredibly important. And there's about 176 different species found in the United States, 3,700 worldwide, and we expect those numbers to be increasing in the United States. So the first one that I'd like to talk about in an impacting factor in these vector-borne diseases is climate and climate change. So a temperature rise will allow for these vectors to grow and move into new areas in which they were previously uninhabitable. So the temperature rise will fit the temperature range in which that vector is most competent and able to transmit its disease. So down here in the left corner, just kind of a general guide of what California might look like. I think we can kind of maybe not ignore the higher emissions, but those are worst case scenario. So lower emissions is a pretty good predictor for what we can look at. With that temperature increase, there's also going to be range expansion. So they'll be moving polewards at, I think it's roughly about 5 kilometers per year is what some studies have been showing. And then also seasonality. Seasonality will be increasing as well with the temperature increase, meaning more months out of the year, the mosquitoes will be able to transmit that vector-borne disease. Another issue is sea level rise. So some Aedes mosquitoes have become tolerant to saline water and have been able to find ways to adapt to saline water. And this could be an issue with tidal flooding in the area of La Jolla and other areas that experience tidal flooding. On top of that, precipitation shifts and extreme events will also have an impact. Now, it's a little difficult to say how a heavy rainstorm will impact it because there's a lot of factors that go into this. And also, California is expected to experience extreme wet years. The extremes are going to go up, and those extremes are going to contribute to the habitat expansion of these mosquitoes. So us as a species, we're incredibly urban. We have adapted to urban environments, or we grew the urban environments, and then the mosquitoes kind of came along secondary and adapted very well within our urban environment. They can find stagnant water in many different anthropomorphic sources. whether that's either rainfall or other urban areas. Studies have shown that they have specifically adapted to host specifically humans and in urban areas. So our heterogeneity or homogeneity of cities is very similar across city to city. So these mosquitoes that are, temperature tolerant or capable in one urban environment are very likely to be suitable for another urban environment because of their similarities between the two. Global travel is a huge issue and has been linked to a spread of a lot of these diseases. I think a tire is a pretty good example, like a used tire, no matter which way you sit it, it can collect water because of the U-shaped interior. So tires being shipped, used tires being shipped across the country, over water, those will contribute to the spread of diseases. Land use changes, this is kind of an important one because we've changed a lot of our surfaces to be semi-impermeable and water cannot go through it. So standing water can arise from those areas in various urban environments. Now, when it comes to predicting how California will be impacted, it gets a little bit murkier because of the complexity of the issue. So what we do know is that California will face small amounts of warming and then longer dry seasons and then also increased extremes. These are challenging to deal with because as you can see here in this photo, the resolution of this has all of San Diego and a bunch of other counties all kind of in one box. So finding meaningful predictions and information that can be found that is useful for policy is not as easy at this scale. So to give you a little bit of a bigger picture on the global scale, I think this image does a pretty good job of describing where the mosquitoes are going to be moving and how they're going to be moving poleward. And this is under the worst case emission scenario. So again, take this with a grain of salt. This is most likely not going to be what is going to happen. It's going to be a little bit less than this. However, you can see the number of months as well as the actual habitat where 1 month per year where the Aedes aegypti can spread its disease is increasing. The amount of surface area of Earth and also the amount of people that it will reach with this expansion is a very large number. Tick habitats are expected to produce or to increase by over 200%. That runs the risk of Lyme disease. Diseases that we have to worry about are Zika virus, dengue, malaria, not so much, but a couple other ones in there as well. But I really like this image. I think it does a good job of kind of explaining the core issues. So what's being done about it? There's a handful of things being done about it. The WHO is very on top of things, and they have a global vector control program where they coordinate with multiple different states and different organizations to monitor the vectors and monitor the amount of diseases that are prevalent inside of those vectors, because not all mosquitoes carry disease. Some mosquitoes do, some don't. The mechanism of that is not very well known, but we are trying to learn a little bit more about it. So different types of climate-driven disease models. I think NASA's working on one, as well as a couple other ones. I think that will be a very important part in determining future predictions for diseases if we can kind of get the climate modeling inside of that as well. So vector control is a big part of it as well. Almost every country has some form of vector control that has vectors. The interesting ones that I found were the ones that involve modification either genetically or physically of mosquitoes and then a re-release of those into the wild. So some male mosquitoes will be treated with a certain type of bacteria or will be sterilized, and so they go into the wild, they will mate and then produce offspring that cannot reproduce. So essentially in some areas, in some cases, that will lead to a reduction of mosquitoes and vectors in that capacity. And there's a couple different ways to do that. Vaccines and treatment, I think that's probably the biggest key of this, because it's a frontline defense. It is proven to be very effective in terms of getting rid of or preventing diseases. So I think looking into different vaccines and treatments for these are going to be an important part. So what can we do about it? I think that's a pretty important question. I always ask myself, what can I do on an individual level? What can I do to make this change? And there's a couple things that I'd like for you to think about. I guess just when you're on your next walk, and if maybe it had rained the day before, or you're in a neighborhood, just pay attention. See if there's any stagnant sources of water, any sitting sources of water that are either in a yard or anywhere where people live. And common sources of those are, as you can see on the screen, so tires, like I mentioned earlier, kids' toys, equipment, anything that will hold enough water. And these vectors only need about like a bottle cap's worth of water, about 5 to 15 milliliters, a very, very small amount of water to be able to reproduce. So a lot of these bird baths, hot tubs, anything that holds water and can become stagnant has the potential to become a breeding site for these vectors. Using DEET, which is an insect repellent, is very helpful. Supporting policy for funding these programs that can get out insecticide-treated nets, as well as different insecticides at a public level would be important as well. And then also on the policy side, so integrating vector risk into climate adaptation planning, I think, is an important one. Having procedures and safeguards in place for when these diseases emerge into new places. We have a proper protocol on what to do about it. There is kind of the biggest thing that I've found in this climate science space is that everyone says decarbonize. And decarbonizing, I think, is a huge part of being an active participant in climate change. And being a good participant in climate change. So I think that's an individual action that most of us can do, and supporting policy and systems that also support decarbonization. So if there's any takeaway that I want you to have here is that this is a very complex issue, incredibly complex. There's a lot of different factors that go into this. An entomologist, an immunologist, a public health official, a climate scientist, as well as a handful of other different expertises will all have something meaningful to add to this picture. So there is a very, very large need for interdisciplinary science, because with normal diseases, you're only worried about a handful of things like a R value, and then like in the gray over there, the other factors. But with vector-borne diseases, there's a whole other organism that's attached to those organisms. So you have to worry about where that organism can thrive, where it can live, where it can't live, in order to be able to actually predict these things on a level which is applicable for policy. So it's pretty interdisciplinary is the only thing that I'd like to have you take away from this. And that is all. Thank you very much.
That was amazing. Thank you.
Thank you.
I have a quick question on your maps where you were time-lapsing and showing 2050, 2080. Mm-hmm. The 2080 South America map, I just kept staring. There was a break where the red the red was hot, but it looks like the Amazon opens up.
Yeah, that's
Do you have
actually,
any idea there? Of
that's actually an interesting point. And you can see that happening in Africa as well. Some of the more equatorial parts actually decreasing in months where the mosquitoes will be able to transmit the diseases. That's because it's getting too hot for the mosquito. The temperature ranges are actually increasing to where the mosquitoes cannot function anymore. So they're predicting a decrease in months where those would be available. Yeah.
So I think within the last week or so, there was some interesting policy issue came up that Alphabet, which is the headquarters, the parent company for Google, is requesting from the EPA to release like 32,000 sterilized male mosquitoes. And so the policy is kind of interesting there. Number one, the approach. Number two, a private sector company that is wants to take the lead there. And I'm just wondering your thoughts.
Yeah, I think that various forms of releasing insects to breed with other insects is a good form of insecticide or vector control. I personally think that that's using fire to fight fire in the best way possible. If done incorrectly, it can make the problem worse. So there are precautions that you need to take when it comes to screening to make sure that all of those males were actually sterile and making sure that you're not increasing the mosquito population. But yeah, I'm all for it. There are potentially unforeseen consequences and side effects that have not been documented, but I think that's kind of the case with every novel interaction.
Great presentation. Thank you so much for the work you've done. I have a question about Chagas disease.
Yeah.
It's a vector-borne disease that causes a lot of problems in Latin America. An epidemiology study was begun some time ago to see if it had spread into San Diego County yet. Do you happen to know the outcome of that study?
I can't remember. I do remember looking at Chagas numbers in California because the California Department of Public Health has released those numbers. In my finding, I don't think it was anything of significance, which means that there might have been a couple, but it's nothing crazy. I don't think I've seen. Maybe a handful, but yeah.